Hello, in this video we are going to be looking at the power rule for integration. We have already discussed how the power of x formula works, but what we would like to do is we would like to broaden this so that we could have powers of any function, not just the constant function x. Now, before we get too much into the weeds of like what differentials are and what the extended power rule looks like, I want to take a moment to remind you about some things that you should know about derivatives. All right, so what we're going to be doing is I want to look at a function and its derivative. So the notation we use for a function would just be f is equal to something, and then its derivative is going to be f prime is equal to something. Now, we know how to take derivatives of any number of functions, but what I would like to look at right now is something like 2x squared plus 3 raised up to the 4. When you look at something like this, taking its derivative would require a use of the chain rule. So we apply the chain rule and we see that its derivative is 4 times the inside raised up to the third. Let's write the inside down, 2x squared plus 3. And then you have to chain on the derivative of the inside. Let's see, so this would be 4x. And then you would, of course, simplify after that to get 16x times 2x squared plus 3 raised up to the third. So this process of going from a function to its derivative down this way is called differentiation. If, though, you have a derivative function and you are trying to reconstruct the original function, when we go the opposite direction, we call this process anti-differentiation or integration. Now, there are two sets of notation that you could use depending on if you are trying to discuss the differentiation process or if you're trying to discuss the anti-differentiation process. If you wanted to find the derivative of a function, you would start by saying, like, I want d dx of the thing. And then because we've already shown what the derivative is, I could say this is equal to 16x times 2x squared plus 3 raised to the third, right? Because I had a function, I was taking its derivative, and I ended with this result. And that's all that this line says. Now, if, though, we wanted to go in the opposite direction on the anti-differentiation arrow, we would start with this function, and then this is going to be our answer. So the way that notation looks is we take an indefinite integral, so it's the integral of 16x times 2x squared plus 3 raised up to the third dx. This integration sign and this differential here, these indicate the process of antidifferentiation. So when you see this notation, all it means is take the antiderivative of the thing that's inside, and because of how we've been setting up like this relationship here, I know the antiderivative of this function is this, so I'm just going to write that down here. It is the quantity 2x squared plus 3 raised up to the fourth. One extra consideration you have to have when you take an antiderivative is you have to add on plus c at the end, just because, so plus c, just because if you did take the derivative of this function, the derivative of a constant disappears in that process. So we call this plus c the constant of integration. Now, if you began with a function and computed its derivative, that process should be pretty familiar to you. However, it would be fairly difficult with our current knowledge to be able to handle this question in red if we didn't already know what the answer is. How do you know what function yields this as its derivative? Well, that is the purpose of the notes for today. All right, so back to the regular notes. In order to be able to expand our regular power rule of x, we need to first of all think about what is dx in this anti-differentiation. So dx is called the differential of x, and then dy would be the differential of y. So when you see dy dx, that would be the same thing as the first derivative. This is something that you are actually able to break apart into, like, thinking about it as dy divided by dx, and that's going to be useful in the next type of thing that we're going to do. But before I show you how it's going to be useful, let's get a little bit of practice using or computing a differential. So let's assume that y is equal to x cubed minus 4x squared plus 5. We know that dy dx, that's the derivative of y, so y prime is equal to dy dx, which would be 3x squared minus 8x plus 0. Now, the implication here, if dy dx is equal to this thing, actually, let me go ahead and erase the y prime, because I feel like that gets in the way of what we want to talk about. You could think about multiplying both sides of this equation by dx to remove it from the left side, and then you would get it on the right side. So dy would be equal to 3x squared minus 8x dx. And if for some reason, hint, hint, nudge, nudge, if for some reason you wanted dx completely by itself, you could just divide both sides of this equation by the thing in parentheses. However nasty it looks, just divide both sides by the thing in parentheses. So if I divide both sides by 3x squared minus 8x, then what I get is dx is equal to dy over 3x squared minus 8x. Okay, so this is the first time we've ever thought about a derivative dy dx as being actually composed of two differentials, but you can do algebra with these two differentials. Now this is going to be eminently useful in the thing that we are about to do. All right, in order to introduce the power rule, before I show it here on the screen, what I want to do is I want to show you a derivative that leads into the power rule. What we start with is we suppose that y is equal to some function raised up to the n. Now, if this was true, we would know how to take its derivative using the chain rule. So what we would know is we would know that y prime, which is the same thing as dy dx, would be equal to n times the function raised up to the n minus 1. Let's go ahead and take the time to write the function u of x. And then afterwards, because this is an application of the chain rule, we've taken the derivative of the outside. We still have to take the derivative of the inside and chain it on at the end. What is the derivative of u of x? It's just u prime. So we would multiply by u prime of x. All right, I'm going to draw these little arrows again. I had a function and I computed its derivative. We call that process differentiation. Now that I have the derivative of a function, if I wanted to go back up here, we would call that anti-differentiation. So to be clear, this was the original function, and this here is the derivative of it. Now, because of this relationship, what we can do is we can write this out using integral notation. The indefinite integral of n times u of x raised up to the n minus 1 times u prime of x with respect to x. So all this is saying is I want the antiderivative of this thing.
Yeah.
What is the antiderivative of this thing? It's this function right here. So I'm going to say it equals this thing up here. Equals u of x raised up to the n. Of course, with the constant of integration added in. So let's see how that becomes the power rule for integration. What we would do is we would divide both sides by n, thereby removing the n on the left, and giving us an n in the denominator on the right. Now, the generic form doesn't start Like because we're starting with this thing, rather than starting with our exponent being n minus 1, we're just going to scale this up by 1, which would scale this up by 1, this up by 1, this up by 1, and this up by 1. So it becomes the indefinite integral, or the antiderivative of u raised up to the n times u's derivative with respect to x would be equal to the u function raised up to the n plus 1 all over n plus 1. Now, there's a lot of ways that we can write our notation. So a different way to write this notation, instead of calling this u of x, we could just call it u. So the antiderivative of u to the n, du, would be, so this is the derivative of u, it would be u to the n plus 1 all over n plus 1, plus that constant of integration. So when we write it like this, we have to be very careful with this du notation, because du really does represent like an entire derivative. All right, all of this has been very heady. Let's get some concrete examples so we can start really making sense of this. First problem I would like to look at is, what is the indefinite integral, or the antiderivative of 3x squared plus 4, all of that raised to the 5th, times 6x with respect to x. Now, what we are trying to do, let me just remind you, your final answer is going to be a function whose derivative is exactly this thing. So there are ways to just kind of like guess and check without using the previous rule. You end up having to use the rule, but you don't have to think about it. You could guess different functions and eventually come up with something whose derivative gives us exactly this. Now, I'm not a fan of that, so what I'm going to do is I'm going to be very systematic with how I approach this problem. I first of all want to identify what is u in the context of this example. U is always going to be the thing that's being raised to the exponent. So in this case, 3x squared plus 4. 3x squared plus 4. Then we know that the rule references du. So what is du? I'm going to start by saying du dx, and we can compute that this would just be equal to 6x. Now, because du is a differential and dx is a differential, we can split these into two parts. We could multiply both sides of this equation by dx, and we would get du equals 6x dx. Now, in some instances, this is directly applicable to the thing you see over here. Like, wow, du is 6x dx, I see 6x dx. And then in this instance, I'm just going to directly apply it. There will be future examples where you don't see this happening in the problem, but we'll talk about that when we get there. So with this, let me go ahead and do a little bit of highlighting. The goal of what we are doing over here is you need to see u in the problem, which I do. You also need to see u's derivative, du, in the problem. But as soon as you have those pieces, what you're allowed to do is you are allowed to rewrite this. So I haven't taken an antiderivative yet. I'm just rewriting this. This is u raised up to the 5, and then everything that's highlighted in blue is actually equal to du, and that makes this problem look like one that we have previously done. So I'll say this is equal to u to the 6 over 6. Remember that power rule of x formula just says you increase the exponent by 1, then immediately divide by the constant. Don't forget to add in a plus c. Now, this seems like, hey, isn't this my answer? Well, it's not quite your answer yet. Your question was phrased in terms of x, so don't answer in terms of u. We do this u substitution just to help us think about it, but your final answer needs to be in terms of x. So I'm going to rewrite u. I know that u is equal to 3x squared plus 4, so I'll substitute that in here. This is 3x squared plus 4 raised up to the 6 all over 6 plus c. So this here is my answer. What I have in my hands is a function whose, if I took the derivative of this function, I would get back to what I have here in like yellow and blue. All right, let's look at another example. So this time, let's find the antiderivative of the square root of 2x plus 3 times 2 dx. Now, like I've done in other problems in the past, I'm just going to immediately convert a square root to be the 1/2 exponent, because I have a feeling that that's going to be easier for me to think about. Then, looking at this, I have a function raised up to an exponent. Off to the side, I'm going to write down what my function is. U is equal to 2x plus 3. That's the thing that's being raised to the 1/2. What is du equal to? Du is equal to 2 dx. So the part I'm skipping right here is I'm skipping this line where you could write du over dx and then multiply both sides, but I'm going to choose to just start abbreviating my notation like this. All right, so I'm going to go and do a little bit of highlighting. I started by saying that the inside function was equal to u, so I have that right here. Then I computed du. Du is equal to 2 dx. You have to have this in the problem or you are stuck. Now, that's kind of true, that's kind of not true. You have to account for this somehow. Now, the easiest way is if you see it in the problem, we can just immediately substitute it out. So let's rewrite this. This is u to the 1/2 times du. Now, because I have the variable matching with the differential, I can actually take the antiderivative here, so we can apply this property. Let's see, we would get u raised up to the 3/2 because we are increasing this exponent by 1. Then you immediately divide by whatever the new exponent is. So divide by 3/2 plus c, of course. If you are dividing by 3/2, this would be the same thing as multiplying by 2/3. So 2/3 u to the 3/2 plus c. And then we'll substitute x back in for u. So I know that u is equal to 2x plus 3. I'll substitute it in right here. This is 2/3 times 2x plus 3 raised up to the 3/2 plus c. All right, we have a function. What is the relationship between this function and the original function that was inside of these integral symbols? The derivative of this function is the square root of 2x plus 3 times 2. Okay, let's do one now where your differential part doesn't match up exactly, and we'll see like what do we have to do if I need to have 2 dx but I instead have something else. All right, give ourselves a little bit more space here. Let's find the antiderivative of x cubed times 5x to the 4th plus 11 raised up to the 9th with respect to x. So we're looking at this here. I see that its some function is being raised up to an exponent, so I'm just going to immediately go over to the side and say that u is equal to whatever the function is that's being raised up to the exponent, 5x to the 4th plus 11. This tells me that du is equal to 20x to the 3rd dx. So the process, if you want to write it out as du dx and then multiply the dx to the other side, you're welcome to, but I'm abbreviating that right now. All right, when you look at this, I have x to the 3rd, I have dx. I can bring these two things together to get x to the 3rd dx, which I have, but what I don't have is I don't have the 20. We don't see 20 over here anywhere. When this happens, there's different ways you can handle it. So some people will go in and they would insert a number, but I'm not going to choose to do that. The way I'm going to choose to handle it is I'm going to solve this differential for dx, and let's see where that would get us. So we would divide both sides of this little equation by 20x cubed, and what would happen here is you get just dx on the right side. So dx is equal to, and then I get du over 20x cubed on the left side. All right, why did I choose to do this? Well, the reason is, okay, let me do all my highlighting. I had an original function that I subbed out for u, and then I took its derivative. And so what I have is I have that dx is really the same thing as du over 20x cubed. Well, I see dx in the problem, and you're always going to have a dx in the problem. So if you've solved this for dx, you can just immediately sub this in, and let's see where that will get us. This will immediately become the antiderivative. Now, I am going to substitute u in for the thing that I highlighted in yellow. So this is going to be x cubed times u to the 9 times, instead of writing dx, I'm going to write what dx is equal to right here. So dx was actually du over 20x cubed. So you're going to notice that you have u's and x's now, which is not good. We only want to have u's at this point in the problem. But you will also notice that the x cubed is going to reduce in a very nice way. So let me go ahead and reduce this. X cubed divided by x cubed would just be 1. So the problem simplifies to be the antiderivative, or the indefinite integral of u raised up to the 9 du. Now I still have this dividing by 20. You can show this a number of places. You can either put it like in your denominator here, like, hey, I'm dividing by 20. Or if you like, you can just put it as 1 over 20. Either one of these options is fine. I'll just show it as 1 over 20, keeping the 20 in the denominator. Now that we are thinking about an antiderivative of u to the 9, we can just do that process over here. We would have u to the 10 over 10. Let's keep the 1 over 20 because that was also part of our original problem, but just it's out in front. It's not doing anything. And what else do we have to have at the end? Every time we take an antiderivative, we have to have that plus c. So let's go ahead and substitute. We'll do two things. We're going to substitute the u back in, or sorry, the 5x to the 4th plus 11 back in for u. And then also we have two numbers in a denominator. Let's go ahead and multiply those together. So what we will end up with is 5x to the 4th plus 11. That's all raised up to the 10. Then we're dividing by 200 plus c. So we end up with this being our answer. And notice, what is the derivative of this? Well, it will end up being this thing in here. It's x to the 3rd times 5x to the 4th plus 11 raised up to the 9th. If you want to take the time on your own to verify that this derivative is actually, the derivative of this function is actually equal to this, you should see that that is true. All right, let's finish these notes out with one final example where the power rule doesn't actually work. All right, let's compute the antiderivative of x to the 4th plus 7 raised up to the 2. We'll do this dx, of course. So what I want us to do is come up with a function where this is the derivative of your function. Well, the way we would do this, we would start by saying u is equal to the inside function. So this is just the x to the 4 plus 7. Then you would have to compute du, which would be 4x cubed, and then you would multiply the dx to the other side. I'm noticing that I don't have a 4 in here anywhere, either in front or at the end. I also don't have x cubed anywhere in here. So my natural strategy would be to solve this for dx. I'm going to divide both sides here by 4x cubed over 4x cubed. So now I see dx is equal to du over 4x cubed. And then now I'm going to reverse substitute things in. So this becomes the indefinite integral of u squared times, let's see, this would be du over 4x cubed. All right, why can we not do anything at this point? In order to use the power rule, in order for this to actually be helpful, you have to have a complete change in variables from all of your starting x's, and you should only have u's in this line. So if you end up with x cubed in a denominator, and it doesn't have an x cubed over here to reduce with, then we're just stuck. That doesn't mean this problem is unsolvable. This problem is actually fairly easy using other methods, just you can't actually do it with this type of u substitution. So let me write this down, like we are stuck. The x's are still here. So if you actually wanted to find the antiderivative here, what you would have to do is you would have to FOIL out whatever x to the 4 plus 7 is. You'd have to actually square that. Then you would get 3 pieces, but then you could just take the antiderivative of each of those pieces individually. All right, hopefully this is helpful as you start to tackle some problems where you get to apply this extended power rule. I'm sure that once you actually get in and start practicing a couple on your own, it will really solidify some of the ideas, and I hope this video is a useful resource for you to reference as you do so.